Okay, so welcome to this 3D printing class. I think we have a large range of backgrounds coming into it, but hopefully everybody will have the opportunity to learn something. Okay, congratulations on putting together your machine. That didn't seem to have gone too badly. About 45 minutes all told to a working machine. Excellent, congratulations. So we can clearly designate you as knowing which end of the screwdriver goes where. Okay. Everybody has a copy of the presentation in front of them, right? Either on paper or on the screen. Lillian, would you like another paper copy?
This is fine.
This is good? Unfortunately, I don't have a screen to project this on, so you guys are going to have to follow along with me and take whatever notes you want. We're going to kind of do this a little bit informally and loosely, so if folks think that I'm going a little too fast, do please let me know. If folks think that I'm going a little too slow, do please let me know. If you want a break, just say, hey, how about a break? And we'll go from there. Yes?
And for format, would you prefer you go through the whole thing and questions are asked, or questions are asked as you go through it?
We're going to be loose and informal, so if you have a question, ask. If I want to finish a thought, I will finish a thought first before I address any question. Right then. Here, Susan, why don't you follow along on this as well? And you might as well learn also. Okay. So, here, page 1, outline. This is what we're going to cover today. We're going to have a little bit of overview of all the major 3D printing technologies. We're going to then focus on one particular technology, FDM, which stands for Filament Deposition Manufacturing. We'll go through the steps you need to go through as a summary. Then we'll delve into the details of one particular piece of software, or actually two particular pieces of software that we use here, not because they're magnificent, not because they're the best in the world or the most popular, but because I happen to like them. And that's really the major criterion. And then we're going to go off and do some printing, and then come back from the printing, talk about troubleshooting, the kind of problems you can run into, what to do about it. Okay? We'll talk a little bit about maintaining your machine and those, the things you need to do, the things you can expect to go wrong with your machine, and what to do about it. Okay? And then finally, we'll talk about sort of the advanced topics to go on to. Just as a heads up, 3D printing is a consumer level 3D printing, which is where we are today. Is a fairly young thing. It's only been around a few years. The machines that are currently available to us are not trouble-free. Okay? The machines that you see in front of you are good machines for the money. If we wanted perfect machines, we'd have to spend tens of thousands of dollars, and they're still not going to be. So, expect that you will have to do a lot of learning. One of the cool things is there is a community around these machines, both on Facebook and on Google. There are folks that can answer your questions. They can help you with ideas. We're here also if you guys have questions. And if something goes south and you just don't understand what's going on, we'll help you figure it out. Any questions so far? 3D printing technologies. Let's talk about the technologies that are out there today. I, this morning, added another page to the proceedings, which I don't have printed, because my printers are dead. Here, we ran out of, toner. But this page right here is in all of your materials. So there are essentially 4 ways of 3D printing something. And they are based on different physics and different chemistry. The most popular one is filament deposition. It goes by lots of different names. FDM, FFF, and everybody and their brother invents their own names for it. And they're all based on a very simple bit of chemistry. There are certain materials called thermoplastic that are relatively inexpensive to manufacture, that melt at a relatively low temperature, and then solidify into a reasonably strong material. The thing about thermoplastics, as opposed to all other kinds of materials, is that they can be melted and remelted and melted and remelted a large number of times before the chemical and physical properties degrade significantly. There are other kinds of plastics. They're called thermosets. Thermoset plastics are ones where once you melt them and they solidify, if you try to melt them again, they will not melt. What they will do is they will turn into charcoal. They will carbonize. Okay? So here are examples of thermoplastics. The most popular one is the one right in front of you. It's called PLA, which stands for polylactic acid, and is a relative of cornstarch and milk. Yes?
Completely not related. Can I just do power off on that machine and turn
Yes,
it
what's
off?
the difference?
It's like making this humming sound.
No,
So I
it's
want
not.
to turn off.
That humming sound is not coming from there.
I walked over there.
Go ahead. Think it out. It won't. The humming sound will still be there. There are other thermoplastics. Some of them you can print with. For example, ABS, nylon, PETG, and lots of others. There are some thermoplastics you should not print with, because as a side effect of their melting, nasty things can occur. For example, there's a lovely thermoplastic out there called PVC, polyvinyl chloride. PVC is in your house everywhere. Wiring is often in your house, often covered in PVC. Lots of piping in your house is probably made out of white PVC. The problem with PVC is that C on the end, chloride. Okay? If you heat up PVC, it gives off chloride. Chloride, for those of you who are not old enough to remember, was used in World War I as a chemical weapon. Okay? There's a clue in there somewhere. Don't heat it. Okay? Anybody tells, ooh, let's print with PVC, run. Don't argue, just run. You know, it's like somebody will tell you, well, we can cut PVC with a laser cutter. Run. That person is too stupid to live. Run. Okay? Just simple as that. You know? It's like when kids wave around a gun. Just run. Don't argue, don't talk, don't say anything, just run. It's easier that way.
Is there somewhere on the net where the various plastics are described and the characteristics and what used them for and that kind of thing?
There are a number of attempts at doing so. They are very disjointed, and you have to do a lot of digging to get to a good picture. We'll talk a little bit about materials towards the end if you remind me. I don't have that discussed here, but we can have that as a discussion sort of on the advanced topics. Okay. In addition to plastics, there are other thermoplastic materials out there. Paraffin wax is a thermoplastic. There are certain paraffin waxes that can melt in as low a temperature as 65 degrees Celsius. There are some that can withstand up to 150 Celsius. So basically, just as an aside, okay? Yes, we live in the United States. Yes, everything is measured in inches and pounds and whatnot, except for 3D printing. Because 3D printing is so popular all around the world, most of the time in 3D printing, everything is millimeters, degrees Celsius, and kilograms. Okay? You don't buy a 2.2 pound spool, you buy a 1 kilo spool. You don't move 4 inches, you move 100 millimeters. You don't heat to 212 degrees, you heat to 100 degrees Celsius. Okay, so when I say degrees, just presume it's Celsius. I will say something, I will actually explicitly say Fahrenheit or F.
Are you guys cool with metric?
Yeah,
I mean, just check it. I come from a generation where that wasn't always the case.
Okay. So, one of the interesting properties of thermoplastics is that they have two interesting, actually 3 interesting temperatures. There is a lower temperature called glass transition temperature, also known as TG. Glass transition temperature is where the thermoplastic material starts getting kind of soft. It's not flowing, but it's soft. It loses its structural rigidity. There is the melting temperature, TM, where it actually runs. And then there's carbonization temperature, TC, which is where it turns into ugly black muck
This stuff that
that's like
goes-
carbonized charcoal and various derivatives. It turns out that it's important to know what the 3 temperatures are for any material you work with. I'll give you a hint. PLA has the following 3 temperatures off the top of my head. TG is about 65 C. TM is about 170, 175 C. Big gap, which is important because that gap is where we live. And we 3D printing people. And TC, the carbonization, is about 250, 240, 250. Right? So, on an airplane, you have 3 kind of speeds. You have the stall speed where the airplane falls out of the sky. You have cruise speed where the airplane is tooling along nicely. And you have VNE, velocity never exceed, where the wings fly off, all by themselves without you. And that's not a lot of fun. So for us, that never exceed is TC, carbonization. You never want to have a plastic in the extruder when that extruder is at that temperature. The reason why is when it turns into gunk, when the plastic turns into gunk, you then have to clean it out. That means you have to disassemble the extruder, drill out stuff, or toss things out the window and get new parts and reassemble. Either way, it's a pain. Don't do this.
How many degrees can you come within that?
You can come within a dozen degrees of that and still be okay. So for example, we routinely, unfortunately, because some people don't pay attention, I've routinely found PLA in an extruder at 230 C and survived. Okay? However, every time you do that, there's a little bit of a deposit building up. You do that often enough, long enough, the deposit builds up inside the extruder and clogs it up, and the machine doesn't print anymore. Okay? So basically, I don't like PLA heated above 205. I print at 205 all the time. A couple of degrees over is okay. Okay? ABS has slightly different numbers. ABS glass transition temperature is about 105 C. ABS melting temperature is about 230 C. ABS carbonization is closer to 300. Okay? Now there's some really wacky materials out there. For example, nylon. Nylon glass transition is about 65 C, maybe even a little less. But its melting temperature is more like 250, 260, and carbonization is well north of 300. The end of all of this is be aware of the properties of the material you're printing with. Act accordingly. Use the material with knowledge and understanding. That make sense?
Okay, let me ask a sort of specific question here, and that is, given those three numbers, what does that tell you about setting bed temperature?
Excellent question. Normally I would address it down further and we'll go over again, but I can answer it easily. Typically you want the bed temperature to be pretty close to glass transition.
Okay, above?
If you can get it above, that's fine. That's good.
Okay.
But you want to get as close to glass transition as you can. Here's why. Molten plastic, when it cools, shrinks. Different plastics shrink different amounts. But all plastics start shrinking when they hit glass transition temperature on the way down. Okay? So if you just melted a piece of plastic, until glass transition temperature, it's not going to shrink that much, if at all. Once it hits glass transition, that's when it starts shrinking. And the further from glass transition, the more it shrinks. It shrinks proportional to temperature. So what the bed does is this. Think about it this way. Like you put down a bead of plastic on the bed, right? It's glued on. Now, you cool it. What happens? It tries to shrink. When it tries to shrink, what it's trying to do is unglue itself from the bed and shrink. This is a bad thing for two reasons. One, if the print is not adhering to the bed, it's going to shift and blow up, and the print's going to be no good. Secondly, what often happens is the edges start lifting up like this. This is called curling, it's also called warping. Okay? This is not good because then you don't have a flat bottom. Okay? So a lot of the problems you run into with printing, with FDM printing, is caused by this exact phenomenon. It's either curling, warping, or unsticking. Okay? If you can solve those problems, your ability to print successfully will go up by a factor of 2 to 5. So we pay a lot of attention to things like bed adhesion, glass transition temperature, and things of that nature. Okay. That's as far as I want to go to in terms of FDM printing. Let's quickly go over the others. Stereolithography, also known as SLA or resin printing, was the original 3D printing mechanism, which was invented about 30 years ago. It is based on the idea, on a chemical and physical phenomenon, whereby if you shine a light of a certain frequency at some liquid chemicals, they solidify in the place where you shined the light.
These are very bright lights, and usually a very tiny point.
Yep. Often a laser. Yep. Sometimes an LED, a light emitting diode. Now, the way this works chemically is this. Plastics, when they're in solid forms, are what are called polymers. A polymer is a long chain molecule that consists of a bunch of identical little chemical subunits that are glued together in a long chain. The process of lots of these little cells or components gluing together is called polymerization. And the result of it is called a polymer. But the cells themselves are called monomers. They're called monomers because there's only one of them, right? Mono. So the process of going from a puddle of monomers to a solid polymer is called polymerization, and it's typically triggered by a chemical catalyst. So the way that stereolithography works is that you start with a goo of monomers, and an inactive catalyst, all mixed together. And when you shine a light on the goo in a particular area, the catalyst turns active. From being an inactive molecule that just sits there, does nothing, slowly, it turns into a chemical catalyst that acts quickly. And the result is that in that area of the activated catalyst, the monomers clump together into longer molecules and create a solid polymer. It's actually really cool.
Messy, right?
Quite messy. We'll talk about that in a second. So, in order to have a SLA printer, you need a vat of resin, which is the monomers mixed together with an inactive catalyst. Okay? You need something, some mechanism to project an image on it, and you need some mechanism for moving the resulting object around in the vat. There's lots of versions of this. They all have some very similar properties. They're typically somewhat more expensive than filament printers. The resins make a god-awful mess, but the nice thing is that resin printers produce results that are much, much finer in detail, in resolution. So,
You can produce details almost as fine as a human hair.
no, much finer.
Finer?
Much finer. You can get down to 5-micron
I
features.
did not realize that.
Oh, absolutely. The better resin printers routinely print better than 10 microns.
What's a human hair?
Well, a millimeter is 1,000 microns. A human hair is maybe quarter that at most.